So this video is going to show you how to do the math in order to determine the order with respect to the reactants and then your overall rate expression with exponents. So we're going to do two different examples. The first example only has one reactant. So it says that sulfuryl chloride decomposes into sulfur dioxide gas and chlorine gas. So what they did was they did a number of different experiments where they changed the concentration of the reactant and then measured the rate of reaction at the start. This way, they can determine how the concentration affects the rate. So our rate law expression for this reaction is R is equal to some constant K. R is rate. Rate is equal to some constant K times the concentration of our reactant to some exponent M. So the whole point of doing this is determine the order of reaction with respect to your reactant, that's the exponent, and determine your rate law constant. But you have to do this in different steps. So what you do is you compare two different experiments where you have changed the concentration of your reactant. So this case, let's just try experiment 2 to experiment 1. So we're going to compare the run 2 to the run 1. So experiment 2 to experiment 1. So we're going to substitute in our values into the rate law expression. So run 2, we're going to plug in our rate this is going to be equal to some constant K, and our concentration for run 2 was 0.3 mole per liter to some exponent M. Now we put it all in data for experiment run 1. So the rate was 3.3 times 10 to the negative 6 mole per liter per second. And this was equal to some constant K times the concentration to some exponent M. Now we cancel what is similar on the top and the bottom. So moles per liter per seconds on the top and the bottom, gone. K, top and bottom, gone. Mole per liter, just the same exponent M, gone. So that leaves us with our numerical values. So 6.6 times 10 to the negative 6 divided by 3.3 times 10 to the negative 6, that is 2. And 0.3 divided by 0.15 is 2 to the M. So our exponent M must be 1. 2 to the first power is 2. This reaction is first order with respect to SOCl2. So now we have to figure out our K value. So now we know what our exponent M is. What we're going to do is we're going to isolate and solve for K. Now we can use any of the reactions in order to solve for this. So let's just pick reaction 1. So substitute in all the values from run 1. So 3.3 times 10 to the negative 6 mole per liter per second divided by 0.15 mole per liter to some exponent 1. And when we solve for this, we end up with a numerical value of 2.2 times 10 to the negative 5, but our units are really important. If we have mole per liter per second divided by moles per liter, that's the same thing as multiplying by the inverse, so liters over mole. So our liters cancel, our moles cancel, we're left with a unit 1 over s, 1 over seconds, or seconds to the negative 1. This is going to be our unit for our K value for any first order reaction. So now our rate law expression is our K value times our concentration to the power of 1. So the decomposition of sulfuryl chloride is first order, and that is our entire rate law expression. If you have 2 or more reactants, you just have to repeat the steps each time to solve for our exponent m. Only this time you have to pick trials where the other concentrations remain constant. So, example 2 will help me show you this. 2 molecules of nitrogen monoxide react with 2 molecules of hydrogen gas, and this forms nitrogen gas and water vapor. A lot of times these reactions will tell you at the temperature at which they occur, and that's because your K value will change with different temperatures. So this one happens at 800 degrees Celsius. So the K value that we figure out will only apply at this temperature. So our rate law expression will be R is equal to K times our reactants to some exponent. We are going to figure out what those exponents are. So if we are going to solve for nitrogen monoxide, we must pick 2 reactions, 2 runs where the H2 concentration doesn't change. That way it will cancel and will not be a factor. So in order to do that, we will have to use trials 2 and 3 because the H2 concentration doesn't change, it stays at 0.2. So if we compare run 3 to run 2, substitute in your values. So for experiment 3, the rate is 8.8 times 10 to the negative 5 mole per liter per second. This is equal to the constant K times the concentration for NO times the concentration of H2. So that's the expression, rate law expression for the experiment 3. So now put this all over the rate law expression for run 2. So the rate for the second experiment was found to be 2.2 times 10 to the negative 5 mole per liter per second. This is equal to K times the concentration of NO forgot that mole per liter, times the concentration of H2. So, cancel out what's on the top and the bottom. K is gone. Mole per liter per second is gone. The units are gone because they are to the same exponent. And then H2 is gone because that's also stays constant. So we're left with 8.8 times 10 to the negative 5 divided by 2.2 times 10 to the negative 5 and 0.8 to the m divided by 0.4 to the m, which is the same thing as 0.8 divided by 0.4 all to the m. So this is equal to 4, and this is equal to 2 to the exponent m. So 8.8 divided by 2.2 is 4. 0.8 divided by 0.4 is 2 to the exponent m. So m is 2. The rate order with respect to NO is 2, or second order. So with respect to nitrogen monoxide, the order is second order. So that means that if we double the concentration of nitrogen monoxide, it will quadruple the rate, because 2 to the exponent 2 is 4. If we triple the concentration of nitrogen monoxide, the effect on the rate would be to multiply it 9 times faster. Okay, so now we've got to figure out what the order of reaction is with respect to H2. So we're going to repeat this, but for the two trials where nitrogen monoxide is constant. So if we look at our table of given data, nitrogen monoxide concentration was kept constant in runs 2 and 1. So we're going to compare run 2 to run 1. So our rate for 2 is 2.2 times 10 to the negative 5 mole per liter per second. This is equal to some constant K times the concentration of NO to the exponent m, concentration of hydrogen is 0.2 all over the rate law expression with rate 1 substituted in. So trial 1, we have the rate, we have the K, we have the concentration of NO, and we have the concentration of H2. So everything is going to cancel except for these. So 2.2 times 10 to the negative 5 divided by 1.1 times 10 to the negative 5 is 2. And this is equal to 0.2 divided by 0.1, which is 0.2, to the exponent n. So in this case, the exponent is 1. So the rate order with respect to H2 is first order. So now we can rewrite our rate law expression. It's some constant K. Concentration of nitrogen monoxide to the power of 2 times the concentration of H2 to the power 1. So now that we have our exponents, we can solve for K again. And what we do is we pick one trial, one run of the experiment, substitute in the values, solve for K. So if we isolate K again, it's equal to the rate over the concentrations. So we're going to plug in our values. Let's pick trial 1. 1.1 times 10 to the negative 5 mole per liter per second divided by 0.4 mole per liter squared times 0.1 mole per liter to the exponent 1. So 0.4 squared is 0.16. So this becomes 0.16. Multiply that by 0.1 and we're left with 0.016, but we've squared our units here times moles per liter here, so our units become mole cubed over liters cubed. You have to do the same math to your units as you do to your numerical values. So 1.1 times 10 to the negative 5 divided by 0.016 is equal to 6. We can round it off. 6.9 times 10 to the negative 4. But our units are going to be a little weird. We've got mole over liters per second divided by moles cubed over liters cubed. So that's the same thing as multiplying by the inverse. So moles reduces, liter reduces. So our units are liters squared over mole squared times seconds. We're going to see some pretty weird units for our K in this rate unit. Okay, so there's your K value. These units are going to be for any reaction that is third order overall. This reaction had one experiment with had one reactant with the exponent 2 and another reactant with an exponent 1, you add them up and you get the overall order of the reaction. So the overall order for this reaction is 3, so that will be our units for any third order reaction. So there's your overall rate law expression for this reaction. So you can determine now the rate of reaction given any value for reactant concentration. Sodium bicarbonate.
And then it's decomposed, turns into Na2CO3. Na2CO3 plus CO2 plus H2.
So the question is, does this follow the law of conservation of mass? What will happen if this follows the law of conservation of mass? What has to have happened?
There will be the same amount of reactants, and the products will be the same. So the number of
So reactants are equal to the reactants, products are equal to the products?
reactants are equal to the products. Total number of reactants.
Total number of electrons are the same. Okay, so how many sodiums do we have on the left? How many H's on the left? How many carbons do we have on the left? No, I'm just asking, how many carbons on the left? How many oxygens on the left? 6. Can't add them. Got to multiply. The reason I'm listing them is because one of our polyatomic ions does not remain as a polyatomic ion on the other side. Carbonate became CO2. So it got a little tricky. So, on the right-hand side, how many sodiums? How many carbons? 1 there, 1 there. How many hydrogens? How many oxygens? 3, 4, 5, 6 oxygens. So this does follow. Another way to do it is to say, okay, I've got 2 carbonates. I've got 1 carbonate here. This CO2 and this oxygen make the other carbonate. So now I've got 2 carbonates. I've got to come up with 2 hydrogens. There's my 2 hydrogens. 2 sodiums, all good. But if you can't see that right away, break it down by atom. Okay. So if you see that, that means heat was used as a catalyst. If you have, sometimes palladium is used as, platinum or palladium is used as a catalyst. You'll just see the element symbols above an arrow. Sometimes sulfuric acid is used as a catalyst for organic reactions. But 99% of the time, they're with the arrow. Not part of the chemical reaction because they don't get used up. No. It's just transformed. Yeah. So next year when we do grade 12 chemistry, I will show you how the universe is a box. When 2 elements or 2 simple compounds combine to make a more complex compound. It's a 6 with an S. It's a solid. Sorry, it's a solid. I'm trying to do this quickly. Okay. Don't be put off by the fact that there's two products. You are making a more complex compound from two simple compounds. The oxygen is an element waste product. So, is this balanced?
No, we need 6, and then the O2 has something, but I have to figure it out.
Yep, 6, 6, 6.
6. Oh, Lord. 6, 6, 1, 6.
Okay, good? So that's synthesis. Decomposition is the opposite of synthesis. So decomposition is the opposite of synthesis. So a more complex compound will be broken down into elements or simpler compounds. Now the thing with decomposition is it needs something else. It needs energy. So this process requires energy. That energy can come in the form of electricity or heat, sometimes even photons of light. So basically, if you have, let's do, magnesium carbonate. Make magnesium and carbon dioxide. Another one. Carbonates will always produce CO2, which is why it's good to have baking soda in your kitchen at home if you're cooking by deep frying. Because if you throw baking soda on your fire, it will end up smothering it because it produces CO2. CO2 is denser than air, so it stays where it is, basically, and it will suffocate the fire. What did I do? Yeah. How's that? Good? Okay, you're welcome. So, magnesium chlorate will make magnesium chloride and oxygen gas. Balance these.